Next problem says point D. Let me point out point D here. Point D is the circumcenter. So again, since point D is the circumcenter, we know the distance. Here's the actual triangle. Let me bold the triangle here. There's your triangle. And point D is the circumcenter of that triangle ABC. So since it's the circumcenter, we know the distance from point D to the corners, to the vertices of that triangle will all be the same. And what this says, point D is the circumcenter. List any segments that is congruent to the following segment. And they ask about AD. We want to know all the line segments that are going to be congruent, if that is a circumcenter, all the line segments that are going to be congruent to line segment AD. Claudia, there's two more of them. Can you tell me which ones they are? Which one? BD? Yes. BD and not AC, but BC. So therefore, BD and BC. Here's why. Once again, if a point is a circumcenter, it is the same distance to all three vertices. So the distance from D to B would be the same as the distance from D to C, would be the same as the distance from D to A. Okay. And again, what could we call that distance? You remember? Starts with an R. It's a radius. Because if you drew a circle around that triangle, that would be the radius of that circle. Moving on. Same thing. You've got D is the circumcenter of triangle ABC. And we want to know what line segment would be the same length as, now this is a little different. What's the same length as BF? I'll give you a second to think on that one. Stephen, can you tell me? Right here. Brianna, can you tell me? No. Hershey. BF is the same length as... Y'all remind me of this from yesterday and from what I said a while ago. A circumcenter is where the three what cross? Thank you. Perpendicular bisector. So that means that this is a perpendicular bisector. This is a perpendicular bisector. And do you see? Well, there's the third one. Let me draw all three of them. This is a perpendicular bisector. This is a perpendicular bisector, and this is a perpendicular bisector. Perpendicular bisectors do two things. Number one, they're perpendicular to the line segment that they cross, and they bisect it. Now, does that help? If DF is a perpendicular bisector, then BF is going to be the same length as which one? Anybody? BA? Here? CF. Somebody said it, I think, in the back. CF. This bisects this. It's a perpendicular bisector, so it cuts it perfectly in half. So BF and CF are going to be the same length. Moving on, AH. Kind of goes along with that last problem. Guys, DH is a perpendicular bisector, so AH would have to be the same length as HB or BH. Okay. That's enough of those. We did that one yesterday. Let's do another one of these like we did yesterday. Once again, a circumcenter is the point where the three perpendicular bisectors cross. So I'm going to pause this for a second while I actually plot these points. Here we go. Again, once a circumcenter is where the three perpendicular bisectors cross. And there's a reason most of the time we give you horizontal and vertical lines. It just makes these problems a whole lot easier. But what you're looking for is you're looking for all three sides, you need the line that is perpendicular and you need the line that bisects all three sides. So let's draw. If I can find we'll use this one this time. We'll do them in green. Okay, a line that's perpendicular and it bisects it. Well, to bisect it, let's see the distance. somebody do the math for me up there. How far is it from here over to here? This is the point negative 8, 3. This is point positive 8, 3. How far is it from there to there? Thank you, 16. So what's going to be right in the middle? Which x coordinate? 0, correct? Because the distance is 16, so therefore half the distance would be 8. And that would be right here in the middle. So perpendicular bisector is what we need. But look, this line moves. Let me show you how much easier I can make this. Why not? I've got a tool right here that draws a vertical line. And what I could just do is this. So then there's my vertical line. So that's the perpendicular bisector. Number 1 is perpendicular. Number 2 cuts it in half. Next side. I need the perpendicular bisector of this side, and I need my horizontal line tool for this one. The distance from here down to here is 8, right? So the middle distance would be 4, so there's that one. This looks just like the problem we did yesterday. And the third side, well, it's slanted, and my perpendicular line is going to be shaped kind of like this, but we already see where it's going to cross. Does everybody see that? It's going to cross right there. To find a point of concurrency. I told you a point of concurrency is where the 3 or more lines cross. Well, 2 of them are already crossing there. The third one's going to cross in the same spot. Really doing the third line only allows you to check your first 2 lines. Because if the third line comes somewhere up here, well, obviously something happened with the first 2. So here we go. Let's try this. This line has a slope of, let's see, 1, 2, well, wasn't that 8? And this was 16, so wouldn't that be a slope of 8 over 16? Which is a half. So any line that's perpendicular to it would have a slope of negative 2 over 1. Then you can find the midpoint. The midpoint's going to be, I can go ahead and tell you right there. So we're looking for the line that has a slope of negative 2 over 1 that has this midpoint. So now I can draw it. 2, where you at? There you go. So there's the picture of your 3 perpendicular bisectors. This is the point of intersection. So obviously that must be the incenter. Let's check it. I have also, under my math tools, a compass. If that is truly the perpendicular bisector, the intersection of the 3 perpendicular bisectors, then I should be able to use that use that circumcenter to draw a perfect circle. I'll go ahead and tell you, it's probably going to be a little bit off, okay? Just because it's hard to get it perfect. But let's see. Is that truly the circumcenter? What I've got to do is I first got to, well, that's pretty close already, isn't it? You got to set your compass to where this is the radius, and I can't open and close my compass through there. So you got to set it to where that is the intersection point, and then let's see how close we are. Pretty close, aren't we? That is the center of the circle that can be drawn that hits all 3 of those points. And yeah, it's a little bit off, but I expected that. Any questions? Just a little food for thought here. How could you use the circumcenter to find the middle of a circular object? Why would you need to do this? Okay, at my previous school, I was head over the robotics team. And at the robotics competition, pretty much here was the rules. They gave you a bunch of garbage, and they said build a robot out of it, and we want the robot to do this. They'd throw in some motors and stuff like that, but it was fun. It's a lot of fun. But here's a problem that we ran into a lot. Okay, you cut out a wheel. Where do you put the hub? Where do you put the axle for that wheel, right? What happens if you put it here? You see where I'm going with that? It's not going to drive very smooth. I'll put it that way. You need to find the middle of that circle perfectly, or you're going to wobble. Your wheels are going to wobble. So what we're doing now, how could we use the circumcenter to find the middle of a circular object? See if this helps. If I took and drew, and it doesn't even have to be a whole triangle, but if I took and drew a triangle inside of this circle, and that's doable. You've got a circular piece of wood and you need to find the middle of it. and you take and you draw a triangle on that wood, what would you do next? Where's the center located? Where the three want from? Find the perpendicular bisectors. Do you have to do it of all three sides? No. Find the perpendicular bisector of two sides. If you want to do all three to check yourself, that's fine. The center of this circle will be, because is that not the circle that goes around this triangle? The center of this circle will be where the three perpendicular bisectors cross. Now here's what you've seen some of your grandparents or parents, anybody involved in woodworking do. A lot of times they'll take and they'll take their, I just went blank. They'll take a ruler, what's called a ruler, but a square, and they'll do this with it. They will draw this, and you can take and actually cut each of these in half. You don't have to do three. You could cut that in half. You could cut that in half, and wherever it crosses, that's the middle of the circle. That makes sense. Again, you don't need three lines. Draw any two lines, perpendicular bisect those two lines, wherever they cross, that is the center of the circle. So there you go. That's next time you need a middle, that's what you do. Your next point of concurrency is called an incenter. Here's what you need to write. Incenter is where the angle bisectors cross. And you can put a dash, and I'll tell you in just a second what's special about an incenter. Now, before we move on, let's go back and talk about angle bisectors. We have to go back, way back for this one. You have an angle, and we're going to cut that angle perfectly in half. That's called an angle bisector. Now, somebody tell me something that's true about if a point lies on an angle bisector. Remember that there? What's true about that point? Equidistant from where? That's right. From the sides. Perfect. It's equidistant from the sides of the angle here. So let's go back to this picture up here. Let's take this. I'll tell you what, let's just clean this. And take this picture. This is an incenter. An incenter is the point of concurrency of all three angle bisectors. Reminder, if a point lies on the angle bisector, it is the same distance from one side of that angle as it is from the other side of that angle. So if this is the angle bisector here of angle C, then this point is the same distance from here as it is from here. But go a step further. B is also an angle bisector. All three of these blue lines are angle bisectors. If a point lies on an angle bisector, it's the same distance from one side of the angle as it is from the other side. So what I've marked, those three red lines are the same distance from the sides of the angles, or the same distance from the sides of the triangle. So now do you see what you can do? An incenter is the middle of the circle that can be drawn inside of a triangle. We can inscribe a circle inside a triangle by finding the incenter, because this distance is the same as this distance is the same as this distance, and we could call that distance, again, a radius. The radius of the circle that can be drawn inside of a triangle. This one says, plot the following 3 points and find the incenter. Now, this is going to be a little bit tougher, because to find the incenter, I need to somehow, and we'll talk about that in just a second, I need to somehow find the angle bisector. And we'll probably use a protractor to do that. We got the points negative 5, 6, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. And I'll pause. What I'll do, here's the 3 graph. Okay. And I'm going to get rid of the graph paper, and then maybe later on I can bring the graph paper back. But for some reason it won't draw on top of it. So we'll try this. Connect it up. Okay, there's my triangle. And again, in order to find the incenter, I need to find the point where the 3 angle bisectors cross. Well, How in the world do we bisect an angle? And I will share with you, there is what's called a construction that you could use a compass and do it. We're just going to use a protractor. Okay, we'll take out a protractor. We'll measure this angle. We'll find out what angle would actually be half of that, and we'll bisect it like that. So let me take out my protractor. Because we need extra practice using a protractor anyway. Undo. Okay, here we go. To use a protractor, first thing you need to do, and on a protractor, you'll always have a little hole right here. You always put the hole on the vertex, and I think we've measured some angles. Can't really remember. And the other thing you need to do is line. Well, first off, let's get that right on. There we go. Get it on the hole, and we've got to line this thing up. There we go. Makes sense. So we're looking at about a 32-degree angle. Everybody see that? So we need to bisect that angle. So the way we bisect it, well, if this is a 32-degree angle, then take half of that, which will be about, let's see, 15, 16, right there. Let me move my protractor. So therefore, if this is a 32-degree angle, 16 degrees is located about right there. So let me take out, let's do it in a different color now. That doesn't look right, does it? Let's check that again. Was it 32? Move it back on there. Put that on there. Oh, where did I get 32 from? Why didn't y'all catch me? I thought that was a 3 right there. It should be about 32. 52. 0, always start with 0. 0, 10, 20, 30, 40, 52. So the middle of that would be more like 26. Does that look closer? Move it. We halved it. Get you a straight edge. This is where you would use a ruler and draw a straight line. That would be the angle bisection. Cuts it in half. Do it again. Come up here. Take your protractor. Let me spin it around. Put the corner of the angle in the hole. Line up the other side. There we go. Line the other side up. And we look and we see, okay, 0, 10, 20, 30, about 38 degrees. So half of that would be right around, half of 38 would be 19, so about right there. We move our protractor, get you a straight edge out. And again, there's another angle bisector. That's enough. You don't have to do all 3. You do a third one just to check yourself. But I can go ahead and tell you this third one's a 90-degree angle. And 45 degrees is going to split it, which is right here, which is going to throw us a little bit off, isn't it? Is that a 90 degree? Thank you very much. Goodness. So I'm making sure y'all are awake. I appreciate that. Notice that 35 would have been disastrous. So there's 45. Connect your dots. And we're pretty close on that one. There you go. So your end center would be right there. And we can see how well that matches up. Let me throw this in the garbage, bring this back. And for some reason now, check it out, it's actually on top of that. It won't let me draw it on top, but it will let do it. -5, 6, let me line it up right. I think it's right there. -1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Yeah. The end center is actually located at -2, 3. Or nearly -2, 3. On your homework, that's what it's going to ask you to do. It's going to give you 3 points, and it's going to say estimate where the end center is, estimate where the circumcenter is, estimate where the centroid is, which is the next one. And here's a good way to check it. Again, if that is a true end center, then that'll be the center of the circle. Let me get my compass back out. That should be the middle of the circle that you can draw inside of this triangle. Here would be the radius. The distance from the center to the outside, there's the radius I'm looking for. Has to be a perpendicular distance. So what I'm going to do, I'm going to take my compass. There's the center, so I'm going to put my pointy edge at the center. I'm going to rotate it around. I'm going to close it where there's the edge. And I'm going to try it. Moment of truth, right? Worked out perfect. That's the center point of a circle that can be inscribed inside of a triangle. Any questions on that one? Probably just going to work one for the next one and then just let you try it yourself. This is, we're not going to do this one, but this is a good application problem. Why would you even need to? It says you want to place a centerpiece on a corner table so that it's located the same distance from each edge. Okay, you want to put it in the middle. It wants to be the same distance from, you want it to be the same distance from this edge as it is from this edge as it is from this edge. In that case, you're looking for the incenter. If you want it to be the same distance from the edge. Now, what's the difference? The incenter is the same distance from the edge. The circumcenter, which we just found, is the same distance from the corners. There is a difference. Okay. Make a sketch to show, and that's what you would do. You would bisect each angle. Let's talk about another way. And I forgot about this. Another way to bisect an angle. If this were a sheet of paper, which y'all be working with sheets of paper, right? Could you not take and to find the angle bisector, could you not take and fold this paper down and line up this edge with this edge? Like look through the paper, does that make sense? Fold it, crease it, cut it perfectly in half, then you would have, that's another way of doing it, then you would have your line that you're looking for. Perpendicular bisectors of RST meet at point D. We're back on old stuff, aren't we? Perpendicular bisectors, I don't know if we're trying to throw both of them in together now. But just keep in mind, anytime a perpendicular bisectors cross, you're looking for you found the circumcenter here. So in this case, perpendicular bisector, this perpendicular bisector. Point D is called a circumcenter. So, what's it saying? Perpendicular bisectors of RST meet at point D. Find DR. I don't know if we're ready for that. Yeah, we're good with that. Does anybody know what DR is equal to? This problem's a whole lot more complicated looking than it actually is. The perpendicular bisectors meet at the circumcenter. The circumcenter is the same distance to where? The corners, yeah. The distance from D to S, from D to R, and from D to T are all the same. So how far is it from D to R? 9. That's all you have to do. Okay. Now, if it said something about the angle bisectors crossing, then it would be then these distances would have been the same. That makes sense. So moving on. That's enough of those. I want to show you how to do centroids, and then we'll stop for the day. Last one. Before we do centroids, we need to explain what a median is. A median of a triangle. This is a new definition. A median is a line segment that goes from an angle to the midpoint of the opposite side. Goes from the angle to the middle. This is actually the easiest one to find. From angle to middle. So therefore, C goes to the midpoint here. B, if you drew another line from here to the middle of this side. Now, how do I find the middle? Well, if this is 10 inches, 5 inches to the middle. If this is 12 inches, 6 inches to the middle. If this is 8, 4 inches to the middle. So if you drew all three of those medians, they would intersect at the centroid. The centroid is the point of concurrency of the medians, and we will tell you what's special about it in just a second. A centroid, therefore, is the point balance. It's the balance point of the circle. Something else that's special about a centroid, and this to me is confusing. Let's word this some other way. If this is your centroid, you have a ratio. We've talked a lot about ratios this year. The ratio of AP to PK is always 2 to 1. What does that mean? AP is double PK. The ratio of BP to PL is 2 to 1. The ratio of PC to JP is 2 to 1. A centroid divides this triangle so that you have a 2 to 1 ratio of one part of the centroid to the other part of the, excuse me, one part of the median to the other part of the median. So with that said, here we go. First step, well, there's a picture of a guy balancing a triangle on his nose. Moving on. Before we find centroids, let's work this problem. It says in triangle ABC on the left, actually below, D is the centroid. DE, this line segment is 6. It says find BE. Be careful here. The ratio of the small part to the large part is 1 to 2, or a 2 to 1 ratio of large part to small part. So if this is 6, I'm looking for first BD. If that part's 6, lost you. Somebody tell me what the red part is. Thank you. And Caitlin, if BD is 12 and DE is 6, they're actually asking for BE. What's BE, Caitlin? Right here. Ethan. The whole thing would be, thank you. There's always a 2 to 1 ratio. Everybody's good with that. If this were 5, this would be 10. If this were 4, this would be 8. It's always 2 to 1. Everybody. Doing another one. P is a centroid. PT is 5. Find RT and RP. We'll do it together. RP, if this is 5, would be 10. That's the biggest piece. And RT would be 15. Reminder. We've constantly drilled this in your head. Hopefully you don't need this reminder. But the way you find a midpoint, because why would we need midpoints? Because we're about to find medians. And medians are drawn from angles to midpoints. Here's how you find midpoints. It should be on your formula sheet already. So let's do one. It says, a performing artist plans to balance triangular pieces of metal during her next act. When one such triangle is placed on the coordinate plane, here's its vertices, 110, 50, 95. What are the coordinates of the point where the artist needs to balance? Got me some graph paper. Let's plot it. So here's your triangle. And again, we're looking for a centroid. A centroid is the point of balance. If we want to balance this this triangle, where would we put that dot that we're going to balance it on? In review, before we actually do this, if you wanted to draw a circle, this is all 3 of the ones that we're doing. If you want to draw a circle around this triangle, you're looking for the circumcenter. And to find the circumcenter, you would do the perpendicular bisectors. You'd find the middle, draw a perpendicular line. Find the middle, draw a perpendicular line. Find the middle, draw a perpendicular line. That's the circumcenter. If you wanted to draw a circle inside the triangle, you would find its incenter. The incenter is find an angle bisector. Find an angle bisector, find an angle bisector. That's the incenter. And finally, the one that we're doing now, we need to find the intersection point of what's called the median. The median goes from an angle to the middle. We like this one the most. Okay? Because to find the middle, this is the point 110. This is the point 95. And the point 50. To find the middle, we simply use our midpoint formula. Sydney, help me with this. We need to find the midpoint of 110 and 95 first. Find the midpoint by adding the x's, divide by 2, add the y's, divide by 2. Sydney, do that for me. Add the x's, what do you get? Divide by 2, you get 5. Add the y's, Sydney, what do you get? Divide by 2, you get 7.5, 7.5. So let's plot it. Let's see if that's true. 5, 7.5. Right there. Yep. And that is, once again, that's your median. Draw it from the vertex to the middle. Now let's do another one. Help me out, Abby, with this one. Let's do 110 and 50. Add your x's, Abby, divide by 2. What do you get? Good. Add your y's. What do you divide by 2? What do you get? So 3 5 should be the middle of that one. Go over 3, go up 1, 2, 3, 4, 5. Looks good. Connect your corner with the midpoint. And you can do it again, you don't have to. Let me show you another trick. You can use slope to find midpoints. If you got this graph, why not just do this? To get from this dot to this dot, you would go up 1, 2, 3, 4, 5, 1, 2, 3, 4. You go up 5 and over 4. Well, to get to the midpoint, why not go up 1, 2 and a half and go over 2? You do it like that. Just half it. If you go up 6 and over 10, we'll go up 3 and over 5. So there's your centroid. So where should they balance it? Right there at this point, which is 5, 1, 2, 3, 4, 5, 5. That's your centroid. That's your point of balance. Any questions?